All right, time for the next talk. Hello everyone, I'm Mikko again from Linaro. I'm talking about secure boot all the way to user space and upstream. And by upstream I mean Yocto upstream. I'm continuing the talk with Trusted Substrate firmware that we've developed at Linaro as a proof of concept for various platforms, providing Arm SystemReady and UEFI firmware interfaces. And then we've had this demonstration operating system on top that we used to call Trusted Reference Stack TRS with a kernel, initramfs and rootfs. And with those things, then we are using or doing secure boot with UEFI and then TPM-backed encryption of file systems. Yeah, so there's lots of slides. This is a copy talk of another talk that I did in the Yocto community. But the building steps of secure boot using standards is to have the hardware to verify the bootloaders and the UEFI firmware with some keys and tied to the hardware. And then for the UEFI firmware with additional keys to verify the kernel, the initramfs, nowadays using the UKI, Unified Kernel Image binary. And then to have the main root file system encrypted or protected with dm-verity. And then using a TPM device to create read-write storage on the target, which is then specific, or the keys are tied to that specific device. And yeah, the encryption happens there. And the keys are not exposed, hopefully. Yeah, so a few words about Arm SystemReady. So it's a nice compliance program from Arm for basically providing the interfaces from the firmware towards the operating system so that we can have a bit generic interfaces for the operating system, that we can use a generic build of operating system on multiple devices using those interfaces. And there are multiple standards classes there which define slightly different interfaces for one of them. One which has quite significant impact is the ACPI support. But I'll come back to that later. Yeah, so running and installing a single operating system on multiple supported devices with different firmware, that works. And it's a good starting point for many kinds of products. You can do secure boot with that as well. But might not be sufficient for all kinds of products, so many vendors end up changing the firmware that they run quite a bit. Then a few words about UEFI. It's a standard interface running on the x86 world as well. Yeah, so there are a number of interfaces for manufacturers to set up things, and then also for the vendors and users to interact with the firmware, for example, by uploading their own custom operating system signature keys and certificates there. Yeah. And the common open source implementations are U-boot and EDK2. It seems to come to many as a surprise that U-boot can do UEFI, but it really can. Yeah, what is secure boot? It's the way for the owner or slash maintainer of the device to make sure that only their software runs on the device. And any modifications to the target software must be detected and the boot must fail. And in the best case, it goes all the way to user space. Everything is covered. In the worst case, it's just a small tiny bit. Yeah, and there's usually multiple levels of signatures and checks and keys and so on to basically create this chain of trust. Few words about the trusted platform module. It's a hardware device which has a private key which is tied to that specific unit. And then it can store data there, and there are ways to extend the data, so-called PCR values, which doesn't overwrite them but only extends to them. And then these values can be used later on to create or verify certain stages of the boot sequence, for example, and for example to unlock encryption of a file system. And there are hardware implementations for TPM, of course, separate chips on the board with various buses, or there is the way to create this inside OPTI as an FTPM and trusted application as well. So it can be a firmware thing which runs. And the term measure boot is the way to use the DPM device in each of the stages in the boot sequence, that every stage before it launches the next one, when it usually loads them as well, it is also using the TPM types to measure the content, basically a checksum of the new binary that is getting loaded and put it into. And when you stack all this up, you get fully measured boot. Then about Linaro Trusted Substrate, like I said, it's a reference implementation for Arm SystemReady IR compatible UEFI firmware for multiple devices. We support QEMU Arm v7, QEMU Arm v8 or Arm 64, AMD KV260, AMD ZCU 102. Unfortunately, both of them without TPM support at the moment. There's a small hardware issue there. Then we have a RockPi and SyncQuasar as devices where we use the Opti FTPM as a TPM device currently. And then we have a Raspberry Pi 4 and IMX8 MP as well, devices there. And we're ramping up with the Qualcomm boards as well. And this work is done in the Linaro Edge computing group. And several of these devices are already Arm SystemReady certified with our builds. We do run the ACS test suite as well every once in a while. Yeah, the major components of the Trusted Substrate firmware is mostly we're using U-boot, then TFA. From meta-ARM, we use the Yocto environment to integrate all these components. And then we have Opti enabled as well. On some hardware devices, then we use the FTPM TA there as well. Some additional features of Trusted Substrate, authenticated capsule updates. We have the lightweight IP stack integrated there with TLS support. So basically we can then download inside the firmware some operating system images and boot into them, including some support for HTTPS as well. Then we have the TPM support enabled as well, but we also have in some build variants the ARM Trusted Services supported. Yeah, and UEFI secure boot is enabled all the way. So we embed some keys sometimes into the U-boot to verify them and so on. And the operating system or the binaries that the UEFI bootloader is loading then must be signed with these keys. So some issues that we don't do currently. We don't do the first verification step from hardware to the first firmware blobs that run. These are the solution, or the problem is that these are very vendor specific currently, and we need to use open hardware where we can reflash the targets quite easily as well. So for any real products, this needs to be covered as well. Then at the moment we are hard coding our public, the signing keys in our Git repo just for easy access or an easy way to build our software stack and also test. And in real products you need to somehow hide the keys somewhere, which is a big problem for anyone working in this space. Yeah, so the place where you do signing usually, I mean, Yocto build is a really complicated one. You maybe should not expose any private keys in the Yocto build environment, so you need to have a separate step where you do signing of the binaries that you build with Yocto, or you have a separate step in the production facilities where you are only then there in that controlled environment exposing some keys and so on for the type devices. And for TLS, I mean, you know, HTTPS requires that certificates have timestamps and they expire sometimes. Well, time support is problematic. Do we have battery-packed RTC clocks on the many devices? No, we don't. So what is the time on our boards when it boots? The build time. Yeah, it's problematic. Time is problematic. Yeah, and then we have both U-boot and UEFI consoles enabled by default, just to enable some of the testing that we do. And in real products, these need to be disabled because you can bypass some of the things there as well. Yeah, so a few words about the implementation that we have in Trusted Substrate. We use Yocto to build and integrate everything. We recently switched over to using several of the software components from the master branches, so we went beyond the current latest releases of everything. And this includes a lot of the stuff from the Trusted Firmware project as well. We use Yocto machine features for all the things that we do. We have secure boot, TPM2 support, Opti support, capsule update support, authenticated capsule update support, all of them enabled with the Yocto machine features. And we are applying some of the patches on top. Some of them are like configuration for like when we need to do some memory setup for Opti and so on. Some of the stuff which cannot be unfortunately upstream so easily. Yeah, and we're pushing our patches, of course, upstream whenever we have some issue that we need to fix. Yeah, and the output of the build is a WIC image most of the time, or a firmware or device-specific firmware image, which we then flash into the ESP, and it also includes an ESP partition with the binary blobs to boot the next steps as well. And as we discussed in the previous talk, we are using the UEFI shell interface nowadays to test an automation with the multiple devices in Linaro Lava to manage the devices in test farm. Oh, so what we have been upstreaming from the Trusted Substrate world already is quite a lot. Unfortunately, the support for the RockPi, Synquaser, and some of the AMD specific bits for the firmware build, we don't know an upstream in Yocto community. It could be the vendor tree, but at the moment the vendors have also so many other features that they care about that what we do with the upstream, U-boot, upstream, Opti, and so on might not be of interest to them. There are certain configurations which could work there, but we haven't been working with the vendors in that area. Yeah, so the SoC vendors, BSP trees are also quite complex, and they include lots of hardware enabler bits and pieces which we don't at the moment care about, so there might be a small conflict of interest there as well. For example, we use the Yocto master branch, and we went to, for example, the U-boot master branch as well already, and the vendors might be stuck on an older release because what they need to support is much more complex than what we do. But what we have managed to do is to basically use meta-ARM as the landing zone for the QEMU parts of our secure boot. So it's there since October last year. So QEMU ARM64 secure boot basically is our trusted substrate implementation for UEFI secure boot. It enables a config snippet for U-boot with some keys as well, and it works. It's tested there in upstream already. So it's a good starting point for anyone who wants to create UEFI secure boot in their own U-boot-based environment. Yeah, here's an example in the CAS configuration how to set up this in meta-ARM. I will not go into the details, there's quite a bit there. Yeah, and it's being tested there in upstream all the time. Okay, then a few words about trusted reference stack that we developed, and which is still the, let's say, the upstreaming base implementation that I use a lot. It's an operating system, it's a kernel configuration, it's an initramfs, and it's a root file system. And the root file system is quite big because it included things like Docker to run various containers and other workloads there as well. Yeah, and we use systemd in the initramfs. I think I have another slide about that as well. So about the secure boot chain of trust that we have. So we have the steps that are actually missing as well. Number one, for the hardware to verify the firmware. Number two, for the firmware to verify the next level UEFI binaries that get loaded, for example, systemd, boot, or grub. We use systemd because it's just easier. There are some issues with TPM support in grub which make it a bit problematic. Then we have the UKI binary, which includes the kernel command line, the initramfs, and that's also signed then with the UEFI secure boot keys. And then what is binding in step number 3 into the user partition, which is basically the root file system, is dm-verity, which is then embedded as a hash into the kernel command line, which is secure boot signed with UEFI. Yeah. Then what is measured boot there? Each of the step, as mentioned before, in the TPM world, before executing a binary in the boot sequence, when it's loaded, they will usually upload the checksum of that new binary into the TPM device, which are then always XORed together to come up with the PCR value. And then that PCR value in certain stages of the boot can be used to, for example, unlock the encryption keys to a root file system. Yeah. Yeah, so the measured boot can be problematic. There are different policies. So depending on what actually changes, every build can be unique. But if only the firmware changes, it might change the PCR values. So if you had previously flashed a device with certain software version, you might need to completely reflash it because of the tiny changes that happened in the firmware, because it changes the PCR values, which is problematic for vendors. What we are using in this prototype is the default from systemd, which may not be secure enough in the PCR policy world for everyone, but that in combination with UEFI secure boot, I think it closes a few gaps that might exist there. For example, the systemd by default, I think it uses only the vendor keys that are used to unlock the PCR for the root file system. It doesn't actually measure everything, but that's a policy that can be changed as well. Okay, then about the Unified Kernel Image UKI. So we did a prototype implementation last year. It has been upstreamed to meta-open embedded meta-open embedded. It's in OE core. It's in poky. There's a BB class to use it. There's the setup instructions how to do that, and basically it combines into a single UEFI binary the kernel, the initramfs, and the kernel command line plus a bunch of metadata and so on, which then can be secure boot signed using systemd-based tooling. Then we had a proof of concept in TRS where we also do the implementation of initramfs with systemd. I'm trying to currently to upstream this into poky as well. There are some issues there, but I'm trying to work on that issue as well. This is because the support for TPM is much easier with systemd, which already has been using TPM devices for a long time in the x86 world, hopefully soon and in the ARM world as well. But the knowledge is there and the defaults will in many cases just work. It's a lot harder to implement these with shell scripts in your own custom initramfs. Yeah, and to create a new partition which is completely specific to a device, you can do this quite easily with systemd repart configuration file on the first boot of the device. And for example, you can copy some files from a template file system and still have a read-write protected access to the root file system. Yeah. And recently a systemd update changed the measured UKI security condition, which is a different beast, which is currently quite difficult to use in the Yocto environment, which is doing fully cross-compilation. Systemd is generating or expecting the device or the initramfs to be generated on the real host after you boot it, and these measured conditions don't work there. So there is a way to work around that as well. Yeah. Then a few words about dm-verity. So I'm trying to upstream the work that I did and the proof of concept. Unfortunately, it's quite difficult. So because I have a dependency, or I want to have the dependency to TPM as well. There are meta security upstream layer which has the proof of concept or the examples in the Yocto community how to do dm-verity. But there are some interactions that you want to have with a TPM device which make it problematic, and I need to have the initramfs with systemd enabled first, which I'm trying to upstream at the moment. Then when developing this, we ran into some issues already, which are, luckily for all you guys, it's fixed already. So when using the firmware TPM device, we had to start the TSupplicant quite early, and because that was the reason, or the reason for that was to have RPMP secure storage available. Because still, as a firmware TPM device, it needs to have a location to store the secret keys, device-specific keys in. And in the old times, there was a need to run TSupplicant in userspace, but it's a bit difficult to run them in the initramfs before you start the init. And then you need to switch over to the real operating system, which makes it even more complicated. But luckily, there's now a kernel implementation of enough of the TSupplicant features to basically get access to the RPMP storage, and the issue is solved. Yeah, Jens did the work there, the Opti maintainer. Thanks, Jens. And the team. Then another problematic thing is how to detect a TPM device. I mean, in theory, it's simple. The standard in the x86 world and elsewhere has been that there needs to be an ACPI table entry for it. And then systemd in userspace in initramfs will detect it and then wait for the drivers to load and so on. Or alternatively, the kernel must have a built-in TPM kernel driver to be able to use it. Sadly, for some of the devices that we support in the ARM SystemReady world, ACPI support is not there. It's not required. And the device trees don't at the moment at least help. Maybe this is something that could be fixed. But there is also another way to detect a TPM device, because the firmware is able to tell the kernel that, hey, the TPM device has a log. These are the entries for the logs, and it provides this interface to the kernel already. Sadly, this is not detected by or used by, it's not visible in user space, first of all, currently. And the systemd is not, as an init, it's not actually checking whether this interface is available from the kernel to user space. Because then it would know that, okay, there was a TPM device used by firmware, let's try to launch udev and load the kernel modules for the TPM device, and then let's use it. So currently this is not a solved problem, and you need to either have the ACPI support, or you need to build the TPM drivers into the kernel. And this isn't a good thing when we have so many different kinds of TPM devices. Another problem is partition auto-detection. There is luckily a standard for this, because the actual, when you are, for example, in Yocto, you're building for generic devices. You don't actually know in which block device your root file system will be, or the dm-verity partition will be in. So you need some way to detect which drivers need to be loaded and where I'm going to find my root file system. So there is this partition auto-detection standard, basically globally known GUID values that can be used. And if you then properly use the TPM encryption as well, then the magic will be just there. It will just work. Same goes for the dm-verity partition detection. If you just hard-code into the kernel command line the dm-verity checksum for the dm-verity partition, it will just wait for systemd to try to load the necessary drivers, and it doesn't matter where it is, as long as the driver is available, the root file system will be correctly mounted. Yeah, and this is then a way to make the initramfs and the kernel and the whole operating system quite device agnostic. It doesn't matter which block device has all the partitions, it will be just found if the drivers are enabled. And then, of course, doing this complicated works, well, there's lots of fun to do with testing. In the Yocto community, lots of the maintainers were asking for tests for various bits and pieces, and they're right. But then I need to also solve issues like when I'm working in the Arm space with systemReady, I also needed to go and fix x86 things. For example, doing EDK2 OVFM updates for the community, even though I'm working for the Arm and with Arm. So, yeah, it's interesting. But this is the stuff that you need to do to get upstreamed as well. There's lots of different details here where things go horribly wrong. In the Yocto builds themselves are really scary if you don't know them, and even if you know them, then you're even more scared sometimes, because really weird things happen. For example, in several of my local testing builds, I suddenly had no bootloader binaries in the ESP partition. There were basically really simple reasons for it behind the scenes, but required lots of debugging in the builds itself to find out the root causes. And then when we're upstreaming these things, it's clear that, for example, meta-security as a layer for lots of security-relevant toolings in the Yocto community, they don't actually have tests currently, or the tests are completely failing, or that the test setup is something that actually doesn't work. For example, the TPM testing that they currently do is using software TPM, which is a pretty nice software component, but they're running them inside the operating system, which they boot into with QEMU, which means that they don't actually do TPM-related activities really properly. We're trying to upstream the solution that we use in the TRS and Trusted Substrate world, where we set up software TPM and QEMU outside the target image, and then we can use the TPM in firmware and do all these encryption and so on steps and measured boot steps really properly when we're testing things. So I'm hoping to get to upstreaming this as well. Yeah. Yeah, and regarding systemd-based initramfs, there's been lots of discussion lately in the Yocto mailing list. I'm trying to get to upstream another revision of the patches. And then there are side problems like how to build less modules in the kernel into the kernel, but instead support for various bits and pieces as kernel modules. And then there's size limitations like all of the kernel modules in the generic ARM64 machine type in Yocto, they are more than 200 megabytes. And if your initramfs is around 300 megabytes, it's a bit too big. So I'm trying to reduce the sizes as well to make the boot times faster and so on. And yeah, then building lots of drivers into or as modules might have issues also, or drivers into the kernel, they actually delay user space boot because in some cases the UDEV is then scanning for several tens of seconds all the different devices that are in the kernel, but are not actually hardware. They're just drivers in the kernel. Lots of issues are interesting. Yeah, so I'm trying to get into upstreaming the meta-security and meta-tpm bits and pieces. The combination of dm-verity with TPM with an encrypted root file system or a partition on the target is a bit non-trivial to set up, and I'm trying to get there, but I need some enablers, for example, the systemd-based initramfs first. Yeah, and as mentioned, keys and building, it's horribly difficult in the build environment to actually handle secrets. Yocto build is, yeah, basically you shouldn't be doing this at build time, but then you need to do them somewhere, and you need to either re-sign the binaries or you need something else. Or, yeah, basically I guess it's an HSM solution at some point, an offline machine where you do the signing, but then how does that work with your CI? You basically need testing keys. And when you have testing keys, you might as well expose them to everyone else. But in the real environments, you maybe need to blacklist those keys because you don't want them end up in production. Okay, yeah, lots of issues there. Maybe someone comes with a really neat solution and shows everyone how it's done properly. That would be nice. Yeah, so my dream is on. Maybe in 25 we'll have an example in the Yocto community how to do secure boot all the way to user space with dm-verity and have a TPM-backed secure storage read-write partition on the target. Out of the box in some of the layers, and then we document it, and everyone will start doing that. And we have secure devices in the field. All right. Thank you. Questions? Any questions? dm-verity. Yeah, so the setup with dm-verity, I mean, I'm not so familiar with all the details of dm-verity. I just need to how it's done in Yocto. There is a sample recipe in meta-security how to do that. There is an initramfs, and you need to have the kernel command line which has to hash to the partition and so on. That works, but then that in combination with TPM, there are some issues there, how it's been done. I think they are Yocto specific at the moment, so it's just race conditions in the Yocto build, which are fun things, as you might know. So there's lots of details, but I mean, I can come back to those as well later on.
Since you are using dm-verity, so I assume the user partition is read-only, right?
Yes.
So do you have a read and write partition?
Yes. So, so the read and write partition is created on the first boot on the device when you have empty space, and I can just configure all the empty space will be a new partition. On the first boot it's being created using TPM device to handle the encryption. And system, it's basically systemd repart is the tool to create this, and all the configuration for this tool exists in the initramfs.
Okay, do you have any recommendation of, let's say I want to run some program inside the read and write partition? Let's say I download the program in the read and write. Do you prevent that, or what's the recommendation?
It's just a root file system, which is read and write. So I'm copying some template etc configuration files into the new partition, but in the first boot, from the initramfs already. And because in the initramfs we've already mounted the dm-verity partition in systemd, and then we copy the template files into the new partition, and then it's just normal read-write storage, TPM encrypted.
I see. Because I read in some work, they prevent program running on the read and write. So the read-only partition can have program, but the read-write don't allow program.
Yeah. I mean, there's lots of things that you can do. In my example, it's just a normal read-write partition where you can do absolutely anything.
Okay.
But it's TPM encrypted with that device that you're running the thing on. So yeah, that's it. All right, one more question maybe, and then.
Did you consider going TPM all the way? Like the dm-verity hash?
No. There's lots of things that can be improved. I want to just have this proof of concept out of the way and somewhere in the community, and hopefully we can improve the things there then. Yeah. All right, I think that's time. Thank you very much.